Okay, so this is question 29 in topic set 7. This question actually requires you to use a few different concepts. There is a Bohr model concept, there is the quantum number ideas, oxidation state, electron configuration. So quite a few concepts that are being placed together in one problem. So let's read through the problem and try to understand how we can solve it. It says you have the following properties for an unknown element. Okay, now I should say it could be several different elements we don't really know. And then it says figure out the element from the properties. So there are 4 different properties given to you. The first one says the neutral atom of this element has 2 unpaired electrons. The second one says one of the unpaired valence electrons in the ground state has an m sub L, which is a quantum number that's equal to -1. And then the oxidation state of this element, or the atom of this element, is +4, the most common one. And then if an electron in a hydrogen atom were excited to the same principal quantum level n as the valence electron in an atom of this element and fell to the n-1 quantum level, the photon emitted would have an energy of 4.9 times 10 to the -20th joule. That last clue actually sounds kind of complicated, but what it is the following. So you have your unknown element and it has a nucleus. The Bohr model, if you remember, has these orbits that are positions that are allowed for the electrons to be found. And in this case, it's saying that when the electron in that element jumps from one level to the level below it, if the hydrogen atom, which can be modeled by the Bohr model, if the electron starts from that same principal quantum number that has a value of n, and it goes to the one that's n-1, in hydrogen that would have emitted an energy of a photon that is equal to that value right there, 4.9 times 10 to the -20th joule. Okay, so let's do that calculations. Energy of the photon in the Bohr model comes from the electron transitions, and the delta E is going to be negative 4.9 times 10 to the -20th. It's negative here because it's releasing energy, and that should equal negative RH, 1 over n final squared minus 1 over n initial squared. Now, in our question, the n final is called n-1, and then the n initial is called n. So we can write the equation that way. Okay, so we can rearrange this equation to make it look like this. 1 over n-1 squared minus 1 over n squared should equal negative 4.9 times 10 to the -20th joules over negative RH, where RH is that value. And then calculating this right side of the equation together should give me 0.022497. Some of you might be thinking this is a difficult problem to solve because I'm going to have to do cross multiplication and some algebra to be able to figure out what the value of n is. That would be one way to do it, but I think an easier way to do it would just be trying out different values of n. So if your n is 7, for example, your n-1 would be 6, and so on. You can try 6 and 5, 5 and 4, 4 and 3, etc. Okay, and if you do that, it turns out that the one that will give you this value right here would be when you start with n equals 5 going to n equals 4. Okay, so this is useful because what it's telling us is that, as the question says, the valence electron of this atom is going to be located in the principal quantum number 5, okay? Because that's what we just found. So in other words, everything in the 5th period of the periodic table, okay? So I have the periodic table right here, and you can see that in the 5th period, you have RB, SR, Y, ZR, etc. And so they are possible choices in terms of the identity of the element. First, I'm just going to write out the different possible valence orbitals. So in the 5s orbital, it could be either RB or SR. And then in the 5p orbital, it could be any one of these elements. And then, of course, the other thing that's in that 5th period is the 4d orbitals. So we're going to use those elements as well. Now, so what we need to do is look at our clues and see if we can eliminate some of these elements. Clearly, there's way too many of them. One of the clues that might be useful is the one that says the neutral atom has 2 unpaired electrons. If you write out the electron configuration for each of these elements, you'll find that Rb and Sr both don't have two unpaired electrons in them. Rb has one, Sr has none, right? And then you can go to the 5p series in this case and just cross out all the ones that don't have two unpaired electrons, which are all these guys right here. So that leaves us with two elements, Sn or tin, and then Te or tellurium. And then in the 4d group, most of these could be removed with the exception of zirconium or Zr, and then palladium or Pd. So I'm going to write them right here, Sn, Te, Zr, and Pd as the four potential elements. The other clue that we were told is one of the unpaired valence electrons has an m sub L equals -1. So remember that that's one of the quantum numbers, the magnetic angular momentum quantum number. So basically, in order to help us use that clue, we're going to have to figure out the electron configuration of these elements that we've drawn out right here. So let's start with tin. So with tin, we're going to have the following electron configuration: Kr, or krypton, and then 4d10. Okay, so that's the D is full in that case. Then we have 5s2, and then the last one is the one that's not full, so I'm going to draw it out. So that's the 5p orbital, and it's 5p2, so it's 1 and 2. And if you remember the 5p orbital, there's three different m sub L values, which is -1, 0, and +1. So in this case, that would be an element that actually has an m sub L equals -1 electron. So that would be still a contender. So we'll still keep this one around. Okay. And then we look at tellurium, which is the next element. And for tellurium, again, going through the electron configuration, we see that it has Kr, 4d10, and then 5s2, and it also has the p orbitals not completely filled, but in this case it's 5p4, so 1, 2, 3, and then 4. Okay, so that's our 5p, and in this case we still have the -1, 0, and +1, but the unpaired electron is located in 0 and +1. So in other words, it's not in the -1, so we can now knock this one out of the contention. So then we look up the other two elements. Zirconium, or Zr, has an electron configuration of Kr and 4d2 and 5s2. So I'm going to keep the 5s2 that's already paired up, and then the 4d2 would be 1 and 2. And then remembering the d orbital, the m sub L values range from -2, -1, 0, +1, and +2. So this one has an electron in the m sub L -1, so we can keep that one alone. And let's take a look at palladium, krypton, and then we would just use the 5s2 and then 4d8. And so again, -2, -1, 0, +1, +2. So we don't really see anything here that belongs to -1, so that one would get knocked out as well. Okay. Now the actual configuration of palladium is actually 4d10, but that also means the same thing, which is that it's not the option that we're looking for. So we're left with these two elements, tin and zirconium. So the last thing we need to look at is that the oxidation state that's most common for this element is +4. So you just need to look it up online. And for Sn, or tin, there's a +2 and a +4. And then if you look at zirconium, one of the more common ones is +4. Okay, so in this case, you have two choices of answer. You can either say they could be either tin or zirconium, or if you just say it's zirconium, that's also be correct, because both of them are reasonable answers to this question.